As we are getting everything ready for a live streaming of this on YouTube, I was going to go ahead and make a couple of general announcements that the people on YouTube don't need to hear. Number one is, hey, these things in your hand right here, let's make sure that you're on silent so that the speaker is not interrupted. That would be great if you would go ahead and check that. Also, if for the banquet this evening, the banquet starts at 7, the social hour itself starts at 6. You do need a ticket, and that ticket will say beef, fish, or other. I'm not sure what other is going to be, but you know, you can mystery meat or something, I don't know. If you don't have a ticket, you probably haven't signed up for the banquet. So you can either see Eileen or Cheslina outside, and they can help set you up at that. And I know I am signed up for the banquet, but I'm not going to be here, so somebody feel free to eat the beef. That will be great. And so this is going to be live streamed in YouTube, and we're getting that ready now, so that'll be great. Kind of let you know how this is going to go. We're going to have a series of speakers. There will be a break as indicated in your program. Each speaker will speak, and there will be 4 or 5 minutes after each individual speaker to ask a quick question or two, but then we'll have a time at the end, about 20 minutes at the end, to have them up here as a panel, and you can ask whatever questions you want, and that would be great. So welcome to the symposium this afternoon on the implementation and use of mechanistic-empirical pavement design. My name is Kevin Hall. I'm from the University of Arkansas. I will be moderating the session today. It's going to be a great session. One of the things I like about this is it really does emphasize this idea that we operate a system, right? It's not just materials. It's not just structural design. It is all of it. And so I think what we're going to hear this afternoon is going to really help us understand how the mechanistic empirical design piece fits into what's going on today. I will say that for the purposes of our audience that is viewing remotely, the opinions of the presenters today are not necessarily those of the Association of Asphalt Paving Technologists, and so each presenter will give his or her own view. We are going to start with Harold Von Quinnis. Harold is with Applied Research Associates. He is going to provide us with an update of Pavement ME design. Help me welcome Harold Von Quinnis.
Thank you, Kevin, and good afternoon. I'm a Texan, so welcome to Texas. As Kevin said, what I'm going to do is give a quick update on the Pavement ME software itself. I'm going to only cover 3 different items. The first one's going to be updating the software, and then I'll go through some of the enhancements that have been added to the software since it was originally delivered to AASHTO, or since AASHTOware took it over, and then a little bit on what's coming next year. So what I thought I'd start with first is acknowledging all the task force members of AASHTOware Pavement ME. Vicki Schofield is the project manager for AASHTOware Pavement ME, and then John Donahue is the chairperson of the task force. So this is simply a listing of all the task force members. Whoops. I wanted to also note that there is a process for updating the software. In other words, what enhancements get added to the software over time. And I thought it'd be good just so that everyone is familiar that it's just not, whatever comes gets made or so. There is a designated process that the task force goes through in making a decision on what enhancements they want to fund or want to add to AASHTOware. And these suggestions for enhancements or improvements are recommended by individual state highway agencies, pavement designers, even consultants. The task force also monitors all the NCHRP, or let's say not all, but appropriate NCHRP projects, FHWA, ongoing agency or pool fund types projects, especially those that have some applicability to Pavement ME. There are some NCHRP projects, obviously, that are designated to add a specific enhancement or capability to the software. And then the task force reviews those, and then they go through a prioritization process each year to prioritize the enhancements of which ones they want to make and when they want to make these enhancements. The task force does have a 5-year improvement cycle or so. This 5-year plan gets updated every year, and some of the enhancements that are a high priority may go into a lower priority and vice versa. So there is a process for that. After the enhancement has been integrated into Pavement ME, there's a specific process that's used to acknowledge that through the community, because the manual of practice isn't updated that often, the manual of practice for the Pavement ME software. That gets balloted just like normal test procedures do through AASHTO. And so there is an addendum that's prepared, and that addendum basically explains the purpose of the enhancement, what the enhancement is intended to do, and how to use the software for the specific enhancement or improvement. There's also, after the software has been released, which is always July of each fiscal year, there's a webinar that's held to basically explain and document or discuss what the enhancement is and how to use the software for a specific enhancement. There's also electronic newsletters that are published and submitted through the AASHTOware for Pavement ME on the status of the software itself, improvements that are being made, and other items that may be of general interest to the users or those that have a license for Pavement ME. A little bit now on the enhancements that have been added to the software over time. And this is simply a listing of those that are specific or applicable to asphalt and or flexible pavements by fiscal year. As you can see, in fiscal year 2018, there were a number of enhancements that were made. These enhancements that I've shown on this slide basically do not include the enhancements that are specific to concrete and or rigid pavements. These are only those that are associated with doing flexible pavement design and or related to asphalt concrete materials. And I'll go through some of these a little bit in more detail because I guess I consider them some of the important ones and the ones that have drawn more interest from some of the users. The first one is just a back calculation tool. Even though it's not an enhancement directly in Pavement ME, it's a tool to help in terms of rehabilitation design and using Pavement ME to do back calculation of layer moduli, and then how those back calculated modula values and other appropriate parameters get entered into the Pavement ME software. The back calculation tool consists basically of 3 different parts. We have a pre-processing part of the deflection data to analyze and evaluate the deflection data by itself. Part 2 is actually the back calculation of the elastic layer moduli. And then part 3 is simply the post-processing of the back calculated values that then go into Pavement ME. The next, which has been a kind of an ongoing, I don't want to say issue, but one of the first climatic data sets were the ground-based, and there were a lot of missing data in some of the ground-based stations. A lot of stations were missing, limited amount of time in terms of climate data. So the task force wanted to expand that to include more years and a better coverage within the United States or North America for the climate data set. So originally, the task force authorized or sponsored a project to include the NOR climate data set, and then within about a year, that was quickly replaced with the current data set the climate data set that comes with Pavement ME, and that's referred to as the MIRA, specifically MIRA 2. The reason for doing that, or the reason that task force wanted that done, is because FHWA and LTPP were going to the use of the MIRA climate data set and were providing it for various pavement evaluation and analysis techniques. So the task force picked up on that and then established MIRA 2 as the primary climate data sets that's used for flexible pavements. They also got requests from some of their international clients because climate was a deficiency and the MIRA internationally, and MIRA 2 is a global climate data set. So it's like for it's a grid point is around the world in terms of providing climate data. And so that's used as the basis for providing climate data and for flexible pavement design. Currently, the NOR climate data set, the North American Regional, I forget what the last R is for, but that is still used for rigid pavement design. So if you have an asphalt concrete or an asphalt concrete surface through Pavement ME, the MIRA 2 is used. If you have a concrete surface, then the NOR climate data set is used. Eventually, even for rigid pavements, the MIRA 2 data set will be used as soon as the next recalibration is completed for rigid pavements. And recalibration, that was a very large enhancement or improvement that was made a couple of years ago. And the rigid pavements have been recalibrated about 2 times since the software was originally released to AASHTOware. The flexible pavements had never been recalibrated, and so this was the first recalibration since the software was released to AASHTOware from NCHRP Project 140D. And basically, but this, on the surface, it looks like there's very big changes to what existed in some of the earlier versions of Pavement ME. The differences really aren't that big of a difference for fatigue cracking, some difference in rutting, and not much for low temperature cracking, but we diverted back to what Matt Witzak originally did in terms of calibrating the original software, and that was to start with laboratory measured values and then apply the beta values as the field shift. Before the software was released, Matt made a decision, or I shouldn't say Matt, the flexible team made a decision to basically combine the laboratory measured values with the field shift. So all beta values in the earlier releases were unity, and those were the local calibration factors. Since many agencies are starting to do material tests in the laboratory, or at least request that testing be done, we wanted to separate laboratory measured coefficients, the K values, from the field shift values, either the beta or the C parameters. And that was basically what was done on this recalibration. The other, another item was resetting the pavement performance parameters. Some agencies wanted to be able to, if they were doing a non-structural maintenance or pavement preservation technique that changed the pavement surface profile, they wanted to be able to take that into account within the design procedure. So the task force made that a high priority a couple of years ago, and so resetting the pavement performance parameters to consider various maintenance treatments or non-structural pavement preventive maintenance treatment was included in Pavement ME. There we go. Now going through very briefly what's coming. There are 3 items. The first is what many agencies have been requesting, and that's the top-down cracking model integration. This is the model that Bob Litton is developing or has developed from Texas Transportation Institute. It's based on fracture mechanics, and that current system or current model approach is being integrated into Pavement ME currently and should be available in next fiscal year, I'd say early next fiscal year. The other item that's coming is what many agencies have also been requesting, and that's the calibration tool, or to assist agencies in doing the calibration. All I'll say on this is it's currently being developed. It will also be released as an assistance tool. It's not directly embedded, obviously, in Pavement ME, but it's an assistance tool or a tool to assist agencies in doing the local calibration. And it consists of 5 parts, and it's also going to be released early next year. A big item that's coming for all AASHTOWare products is moving the desktop Pavement ME or desktop application to a web-based technology application. And this is going to affect all AASHTOWare projects. Pavement ME, I think, is one of the first that's being transferred over from a desktop to a web-based technology interface. We're currently working on that, and it's due to be released in fiscal year 2022, approximate time frame. I've given or shown in this slide some of the steps and processes that are being made. We started this about a year ago, and we're heavily involved in now moving it from a desktop application to a technology application. And you can see the timeline for the 4 major steps that are ongoing. We've completed the first part, evolving the legacy software to the new architectural, and we're into integrating the evolved system with a new platform. This is more IT. I'm not an IT person, so I'm going to be very brief about that. And basically, that's the update. So I'm going to turn it back over to Kevin.
We've actually got time for a couple of quick questions.
Gail Page, consultant, quick question. How many states are actually using Pavement ME routinely?
Okay. I started to put that slide in there, but I took it out and said I probably don't have time to go through all of them. There's probably a half a dozen, Gail, that are using it on a day-to-day basis. There's probably another, I would say, dozen that are in various stages, getting very close to adopting it and using it on a day-to-day basis. Yeah.
Eli Haj, University of Nevada, Reno. Thank you, Harold. For the assisting tool that you mentioned, is that going to be provided for free with a license, or there will be additional fees?
That's a very good question. I know the task force has been discussing what's to be provided with the license and what needs to be provided at an additional cost. I think right now it's going to come with a license, so no other cost, with the exception that depending upon an agency that may, you're talking about the calibration tool, right? Yeah, that may be doing a lot of calibration. We got a lot of data up in the cloud going on, that there may be some cost to the storage, that type of thing. So I know the task force is very sensitive to cost because everyone is sensitive to cost. And I think right now the discussion is let's try to keep it within the cost of the license.
And that tool is for calibrating reflective cracking, fatigue cracking, or is it specific for a given distresses?
It's for calibrating all the distresses predicted by Pavement ME, both flexible as well as rigid. There is a calibration database. And so you might, a lot of local agencies have their own database. You will be able to supplement, or the intent, and we're moving that direction, is to have agencies to be able to supplement the primary database with their own data and use that in their local calibration. But there is a primary database that was used for the original and revised global calibration that agencies will have access to. Obviously, most of those sites are long-term pavement performance sites in the U.S. and Canada.
Very good, thank you.
This is Amin Kutai from Michigan State University. Did I hear you correctly? Did you say when you moved from 2.3 to 2.5.3, the calibration coefficients, there was no significant difference in the predicted distresses? Is that what you just said? Or
No, obviously there's differences, and depending upon what thicknesses you're at and pavement structure, some of the differences can be more significant than others. The big difference is when agencies were originally using, let's say, version 2.5 and earlier, they were all getting very high predicting rut depths in an asphalt concrete pavement, and those over predictions of rutting should be a lot less. There are some of the bottom-up cracking that some of the thicker sections, or let me state it differently, the sensitivity of thickness to the amount of fatigue cracking you're predicting with pavement ME decreases. So thickness is not as sensitive as it was in earlier versions of pavement ME, versions 2.5 and earlier. And one of the reasons for that, if you look at a lot of the LTPP projects, the SPS ones, you're going to see that less sensitivity. And we used a lot more of the SPS ones and SPS 5s for the recalibration that was done in, I think, fiscal year 2018.
will there be any document in the future
There is.
describing why there is a move from?
There is a document within the task force. There's sections. One is for rutting, one's for transverse cracking, one is for fatigue cracking, and one's for IRI. Those are available. They have not been, I would say, publicly released to date, and the reason for that is we were trying to get top-down cracking included in addition to bottom-up cracking. And there was an issue with bottom-up cracking on the fatigue side, which was only recently kind of resolved. It didn't really change any of the coefficients, but the definitions changed a little. So all of those will be available after the next meeting with the task force, which is at the end of this month.
Thank you, Harold.
Thank you.
I'm going to call John Harvey up to the podium. John is a professor at the University of California, Davis, and director of the University of California Pavement Research Center. Been doing that for a very long time. He's going to talk to us about CalME, Mechanistic Empirical Design Tool for Asphalt Surface Pavement. Take it away, John.
Thank you, Kevin. Thanks for having me. I guess it's the button that goes to the right. There's no green ones. Oh, well, we'll try it. Okay, so I'm going to talk about California Mechanistic Empirical Design Tool for Asphalt Surface Pavement. Whoop, don't click it so hard. All right, I think I got it. Okay, why was CalME developed? Caltrans adopted mechanistic design in 2005 in what they call a deputy directive, with the title shown there. At the time, we calibrated and adopted MEPDG for jointed plain concrete. There were some perceived limitations of the MEPDG flexible models at the time. 98% of the money that we spend is on overlaying cracked and jointed concrete and cracked asphalt. Our main distress mechanism in the state is fatigue cracks. So we needed a reflection cracking model. About 70%, 80% of the surfaces in California are rubberized hot mix, and we needed to have a method that would deal with our rubberized hot mix. We felt at the time that the MEPDG seemed to be, no reflection cracking model was focused primarily on new pavement design. We had an APT program at the time, and we wanted to be able to use our APT program to calibrate the model, so we needed an approach other than Miner's Law to be able to calibrate using our APT data. And we were finding a lot of issues at the time with the software, which have been resolved in the meanwhile, but we definitely had some thoughts about reliability that we wanted to look at, and we wanted to be able to run Monte Carlo simulation. And that was not possible at the time, primarily because EICM was running inside, which was slowing the software down. So we had an opportunity to produce, calibrate, and implement an alternative set of design and analysis models for asphalt pavement, which is CalMe. Okay, version 1 was introduced in 2006. We're on the current version of 2.0, which is also a desktop approach at this point. The focus of everything we did was on rehabilitation and preservation. We use what's called an incremental recursive approach. How many have heard of an incremental recursive approach? Okay, so let me explain it briefly. And the main idea for this came from Per Ulitz at the Technical University of Denmark, and he was a major driver for much of the technology that we used at the beginning. So basically, I'm going to compare this in a minute, but in incremental recursive, you start with the initial properties of the material in terms of aging, damage, and fatigue damage, and permanent deformation. In the first day, hours of the first month, you apply loads and you damage the material. You adjust and you age it. You adjust the stiffness of the asphalt based on the aging model and on the incremental damage that occurred. For the next set of loads in the next hours, you update the damage. You proceed through every month of every year updating the damage. So what you should have, if the models are working correctly, is that you should be able to actually predict the damage in terms of loss of stiffness, change in stiffness due to aging, and permanent deformation for each month of every year through the entire life of the pavement. So that's basically what that says there. The response, we're using layer elastic. We're using regression models for the reflective cracking strains. We use the same approach for fatigue of reflective cracking as we use for bottom-up fatigue cracking, except we predict the tensile strains using regression equations, which are run through thousands of finite element runs. The damage models are shown here. They include asphalt fatigue, bottom-up asphalt permanent deformation based on shear stress and strain, full-depth reclamation damage. We've got the foamed asphalt done. We're working on the cemented and engineered emulsion right now, and cold in-place recycling and cemented soils, looking at both fatigue damage from the bottom up and crushing from the bottom down. Sorry, I've been teaching 2 classes and 10 hours of meetings a day, so I'm losing my voice a little bit. The distress models, then, we calibrate we simulate what's happening with the damage, and then we calibrate the damage to the asphalt cracking and the unbound layers ready. So aging and rest period models are included for the asphalt. We knew historically from the shell method that shift factor can vary greatly depending on the rest periods between the traffic. We wanted to account for that. It's not well calibrated yet, but we do have a model that accounts to some degree for that. Primarily, it helped us look at the difference between heavy vehicle simulator without stopping the loads and test tracks, which have rest periods between the loads. We're calibrated for 27 heavy vehicle simulator sections, West Track, some sections from the NCAT track, Men Road, and the SEDEX track in Spain, and 4 California field sections. We use Monte Carlo simulation for reliability. The definition of what is reliability and which variances we consider in that. Right now we're primarily looking at within project variability and then looking at sensitivity analysis to look between projects considering different contractors and material sources. Although that's something we're looking at for version 3 right now is revisit those definitions. A fundamental part of this was the development at the same time of a back calculation program, because we primarily are dealing with existing pavements. We want to rely on deflection back calculation to characterize those, both in terms of variability of the underlying structure as well as the materials properties. So CalBack was invented as a sister program that goes with that. And CalBack loads directly up into CalMe, gives you your materials properties, and also gives your variance of the stiffness, which is considered in the Monte Carlo simulation. Step one of the calibration procedure is to calibrate the damage models. If we don't get our basic approach is if we don't get the damage models, if we can't predict the change in stiffness, then we don't really want to go to trying to predict cracking from stiffness. So we calibrate the damage models using back-calculated actual AC stiffnesses from the test sections. That gives us our damage and aging effects comparing in the wheel path versus deflections taken to the side that only have the aging part going, fit the damage parameters, and then compare those. The basic parameters, like Harold was saying, the basic parameters are developed from laboratory testing, and then we adjust those for the damage process, and then we have a separate shift factor to take us from damage to cracking, which is the second part. Incremental recursive versus Miner's law. So we characterize the material in terms of the damage process for different strain or stress levels, depending on what's critical. We then simulate the damage process for the entire life, each data acquisition time that we do. Then, once we've got the damage models done, we correlate damage to distress, and we calibrate the damage process using the entire, every data acquisition we do through the entire damage process. So every time they went out on WestTrack and did back calculation, that's a calibration point. The next time they go out, that's a calibration point. We calibrate the entire process. With Miner's law, which was actually what we used in our precursor to this, we basically characterize the material in terms of repetitions to failure and end state. And then we look at potential paths to that end state, which occur across the first year. And we get our big N from that, our various big N's, and then we estimate the little N's, the traffic that's coming, and look at that damage ratio. And then we have to calibrate to the end state. To be able to calibrate a Miner's law, you have to have carried every one of your sections to the end state, because otherwise you don't have a data point. You have a right-hand truncated data point. So one of the other things we knew from our APT is not all of our sections failed. Not all the WestTrack sections failed. Not all of our APT sections failed. But we can still calibrate the damage process on every single section without biasing our data set by eliminating those that didn't get to the final cracking end state. Now the little green light's on. So this is an example. I'm afraid to push the pointer here, but I'm going to try it. No. Okay. So in this, the red values are the measured values, and this shows the deflections at the top on the surface of the asphalt, and then the other two show the deflections at the top of the base and the deflections at the top of the subgrade for an example test section. So every one of those is a data acquisition point through the entire life of one test section. What we then show is the calibrated damage process, where we're using, rather than one data point for this test section, from our initial estimates of what will happen in the first year and then taking that out to the end state with Miner's law, and we're fitting that entire curve of the damage process. And then we do the same thing once we've got the damage process nailed down. We take the development of cracking from the initial cracks and then through the progression of cracking as a second model. These were our calibration factors from the HVS test sections and from WestTrack. And this is for the damage. And you can see a range of shift factors. So what we're using in the software right now is the average shift factor across those. What we're damaging actually is the master curve, and this is an actual original intact master curve, and we apply the damage omega to the alpha in the MEPDG stiffness equation, which is what we're using for our master curves, and that basically shifts the curves, the master curves down. So every time we put traffic on, we damage that and rotate that down based on the simulation calibration with the damage process, or if it's aging, we're also shifting it up. So the net for each increment is the net of the aging and the damage. How do we step between these? We use a time hardening process, which basically assumes that damage is irreversible. We've cross-checked this a little bit with a strain hardening process, which moves the other direction as we move between damage curves. Some change in the result. This was the assumption that we went with, which is no reversal. We're accounting for whether we want to call it thixotropy or healing through our rest period function, which is an adjustment on our shift factor for the damage to the cracking parameter. I'm sorry, on the damage parameter. Time hardening, by the way, has been around. Carl Monosmith suggested that from research that was done with Pell and so on back in the 60s. For reflective cracking, we're using the same approach as the bottom-up fatigue cracking, except that the HMA bottom strain is from the finite element via regression equations. For HMA on HMA, we're using the average maximum tensile strain at the crack tip. And for HMA on PCC, it's the bending strain at the crack tip, assuming local debonding of about 100 millimeters on each side of the crack, which comes from our colleagues at Tongji. And we're using thermally induced strains using models from the University of Minnesota. This is what one of my colleagues calls a confusogram. Okay, let me move on. No, this is the top is the regression equation through the finite elements. The main point of this is look at the variables that are in this. These are variables that we have very good data for. And so this was finite element run 2D. We calibrated the 2D to 3D, developed the regression equation, and calibrated that equation for the damage process. For pavement temperature, we have a lot of climate zones. We're using EICM runs, but we're not running EICM. We use a 1D fast thing that goes in and gets the surface temperature out of our EICM database and then comes up with a temperature profile. And we've calibrated this and it works extremely well. And this is super fast, which allows us to run Monte Carlo. So what we can simulate, this is one example. We've also programmed into this that you can build in your pavement preservation triggers to trigger based on damage, cracking, or time-based maintenance and actually simulate the entire process over 40 years. Current stat, I missed one? Yeah, okay. We have a lot of way in motion built into there so that the local folks can do their class 9 to class 5 counts and predict an axle load spectrum based on regression through 115 WIM stations. I talked about the process, the simulation processes. So the way this works now is you can run, say, 100 Monte Carlos simultaneously, walking through the 40-year analysis for all 100 of those in about 10 minutes. Current status, this is primarily, Gail, I'll answer your question before you ask it. Primarily being used for AC long life. It's in the highway design manual that any design for 40 years or longer or a high TI, a traffic index, has to use CalMe. Caltrans, we're just learning. We haven't had any money for 6 years. Nobody even remembers how to do the VIM R-value design. We're fixing that software, getting that out. We're now starting to get $2.5 billion more a year for maintenance and rehabilitation based on our gas tax. And we're expanding this. We are web-based. We're beta testing the web-based version 3 right now. And thank you. Oh, if you're interested in trying out version 2 or by this summer version 3, contact me, please. Thank you.
Mansoor Soleimani, Penn State
Mansoor.
University. Hi, John. Very, very good, John. Thank you for sharing the information with us. On temperature, during your presentation, I was just thinking, okay, where's the temperature model? Hardly simulating the temperature within years.
Right.
Then you had one slide. You went through that so quickly and you said you don't use the EICM.
No, we ran EICM for our climate regions. We used our major stations, made sure we did a whole statistical check for each of our, at the time, 9 climate regions, and make sure we even had to go to Reno to get one of them. But we used our major climate, made sure we had good statistical data sets. We ran EICM, spent months running, and then we go into that database to get the data.
Okay, so as you are simulating it through time, through years, you still go and pull up the data for 2 years? Okay.
So we have 30 years of data. A part of our Monte Carlo is the order in which the years appear. Is changed based on different runs. So that's how we're bringing some variability in the climate.
Good.
Eli Haj, University of Nevada, Reno. Thank you, John, for the quick update. You went through the reflective cracking model. It was a little bit quick. I couldn't capture it all.
It was all a little bit quick. I coffeed up before we came out
But
here.
if I notice that the modulus is part of it, how do you intend to capture the effect of different modifications of the binder or modified mixes with the calibration factor?
I had to cut those slides out. So this is operating off of what we call a standard materials database. So we've actually gone out and we have kind of an ongoing program to get representative materials around the state. We are not predicting properties based on empirical equations, based off of mixed design. So we actually have gotten mixed designs, tested them, and put the parameters in there. We're working out a strategy. We can't test every mix, and they're all changing. We're all going to high wrap right now. Things are changing. So what we're looking for is enough of a set of representative mixes that a designer can look across that set, and that should get regional once we can get PRS implemented more fully. This will start feeding itself. But we use representative mixes, and then we're asking them to do a sensitivity analysis with different mixes meeting the same specification.
But the coefficients will remain the same that you have in the equations?
For a
They might
general
change.
user, yes. For an expensive project like an AC long life project where we're actually specifying with performance-related specs, then we make the contractor do the design based on the PRS and
Check.
yeah, we set a baseline by testing regional mixes, and we use that to set the baseline for the PRS, so we don't set it too high so nobody can hit it or too low so that everybody can hit it. And then that all goes into the database as well.
Very good. Thank you.
All right, thanks.
Thank you so much. Thanks, John. Okay. So our next presenter is actually a paper. This is Virginia's experience with MEPDG implementation. The presentation, the authors are listed in your
how to use the software and where you can find the inputs. All these things are in the user manual. We thought this was an important step for our payment design staff. So one document, they can find everything. The other thing what we did is, in the software Astro Pavement ME, we created a database, and all the material properties are available in the database. So our payment staff, let's say they have to input the material properties for aggregate base. What they have to do is go in the software, go in the database, pick V dot aggregate base, click on that, and they will get the properties. The only thing they have to input is the thickness. So what we thought that will reduce the error for inputting the material properties. For all the material properties, we have the same database. And also the local calibration coefficients we pre-installed in the software, so they don't have to change the local calibration. The next major important step is the training. We started training our payment staff from year 2010 onwards. We used both VDOT and external industry experts for training. Thanks to Harold and Professor Mike Datter, they came to Virginia several times to give training to our staff. Our training not only focused on how to use the software, but the fundamentals, how the payment ME works, what are the models, how they developed, what are the sensitive inputs, and what factors influence the design. And let's say if a design fails, what are the adjustments you have to make? So those are the things we focused on training. And also before implementation, several years, we used Pavement ME as a shadow design. That helped our payment staff to keep working on the software instead of changing one day to a new software. So they have been well equipped before implementation. Now I am talking about the challenges. Astro 93 empirical design was easy. You only use a layer coefficient. For Virginia, we use a layer coefficient of 0.44 for asphalt, and for the aggregate base, it's 0.12. So that means 4 inch of asphalt base is equivalent to 1 inch of asphalt. Aggregate base is equivalent to 1 inch of asphalt. MEPDG don't have this linear relationship. So it changed everything. So I'm going to discuss in the few slides what are the issues we are seeing. The other main issue is, like Harold mentioned, every year Astro releases a new version. It's not very uncommon. because the software is still going through some of the enhancements. But for a DOT perspective, it gives some challenges because we have to work closely with our IT department every time a new software version comes to install. But some of the issues we found is the insensitivity from the contribution from the aggregate. This picture, which shows three cases with a no aggregate base and aggregate base with a different modulus values. And you can see that you can pretty much remove all the 6-inch aggregate base with a 0.5 inch of asphalt. So this has been concerned with our aggregate industry. And what we did is we mandated the use of 6-inch aggregate base. That's our experience. I mean, we have been using aggregate base. It's a construction platform. So we mandated the use of 6-inch aggregate base unless we use CTA. And we are waiting for the NCHRP 1-53 study Professor Bob Litton from Texas A&M is doing. We are waiting for the results. So hopefully the future MEPDG versions will accommodate the new models. Same thing with the subgrade sensitivity. And if you are familiar with AASHTO 93, subgrade modulus was very sensitive, but the AASHTO pavement ME, it's not very sensitive with the different subgrade types. So we haven't changed anything. We are still waiting for the NCHRP study to make changes. The other thing is semi-rigid, modeling semi-rigid pavement and recycle layers. Like I mentioned, we use a lot of cement-treated aggregate. Also, we use cement-treated full-depth reclamation. So the version currently we are using is 2.2. So after this, there is one more version released. But the version 2.2, it's very insensitive to thickness and also the modulus values for semi-rigid pavement. I mean, if you input the CTA modulus or thickness, different thickness, it's very insensitive. So what we did is we modeled as an aggregate base, but we use a high resilient modulus, 80,000 PSI, both for cement-treated and FDR case. For recycled section, both cold-in-place recycling and cold central plant recycling, currently we are not using MEPDG. There's a challenge in using that because when you use both CAR and CCPR as a flexible layer, you have to, like Harold mentioned, the pavement ME is very sensitive to the air voids and the asphalt content. And the bottom of fatigue cracking model uses the bottom layer. So in this case, it will be a CAR. And if you, in the field, usually you get higher air voids for the recycling section, so you have to be careful when inputting. The other thing is sensitivity to asphalt mixes. So we developed only one calibration factor for the asphalt mixtures. When we use SMA mixtures, it predicted very high rating. So that is against our field experience. This is because usually SMA mixtures have higher binder content, and when you test in a conventional dynamic modulus testing, it gives lower modulus. So in turn, it will predict higher rating. So we plan to develop mix-specific coefficients for SMA in the future. The outreach is very important. We formed a technical working group which members from VDOT, both industry, asphalt and concrete pavement, aggregate industry, and federal highway. And we discussed all the issues and came up with solutions. So we got their support. That was very instrumental in the implementation. And also we trained our local consultants. Some of the lesson learned, we need, for the implementation, we require all the help from all the different divisions within the agency, like material, maintenance, construction, and also we need industry and external stakeholders support. Training is very important factor, and what we thought was developing a user manual was very instrumental in the success. And the local calibration is key. Sites need to have certain level of distress. We need to develop a well-established database, so whenever the future version comes, it's easy to do a local calibration. And we need to have both short-term and long-term plan. Short-term plan, maybe how to update the ME user manual, and future long-term plan, how often we have to do local calibration, how often we have to characterize the materials or traffic inputs. Those are the long-term plans. And the future step, like I mentioned, currently we are using for new construction or reconstruction. So we wanted to, most of our work is on rehab side, so we wanted to use this in the rehab design also. And we are currently working on more material characterization. And we yet to install the new version. And before that, we have to do a lot of sensitivity analysis. And Harold mentioned the climate change. And we have to do a sensitivity analysis for what are the changes that brings. With that, I would like to acknowledge VTRC researchers and our materials maintenance division, our district materials engineers. And thank you.
Amir Golalipur, FHWA math program. Good presentation. How are you? Could you please go back to slide number 10? You were showing the global and also local calibration for your
Is that slide number 10?
Yes, please. So, perfect.
Yeah.
So definitely with the global calibration, you can see that the prediction is completely off.
Yeah.
But after even you do the local calibration, still you see a lot of mixes that your prediction is way off than what you're measuring. So do you know what the steps you need to take to get those numbers on the conservative side rather than on the right-hand side of that curve?
Like I said, we did not do a detailed forensic investigation of all these sites that we selected. We did not do, and 78% of the sites were less than 2% cracking.
Mm-hmm.
So only very few sites are way off.
Yeah, there are some of them I can see that they're at 25%, but the predicted one is less than 5%. Is there a possibility that those are a specific type of mixes that is showing that in the model versus the actual measured ones?
I don't think so, but it may be due to different reasons. Maybe it's a debonding. The other type of distresses are present in that particular sections. Like I said, we did not do a detailed forensic investigation of those sites. There may be several reasons. Maybe materials, maybe some other distresses.
Maybe it's worthwhile to look into it, see why they are that off.
We did not do because, like I said, 80% of the sections were less than 2% cracking.
Yeah. Thank you.
Yeah. Thank you. Thank you.
Okay, so our next paper, our final paper before a small break, Xing Hu is a associate research engineer for the Texas A&M Transportation Institute. He's bringing his paper with multiple co-authors, implementation of Texas Mechanistic-Empirical Flexible Pavement Design System. And so, Xing, if you would come up, help me welcome Xing Hu.
Good afternoon, everyone. First, I would like to thank AAPT to provide me this opportunity to make this presentation. And before I start, I would like to acknowledge my co-authors, Dr. Asif Rahman, Dr. Jun Zhang, Dr. Fujie Zhou, Mr. Tom Sculling, and Dr. Inad Mahmoud. Make it work.
Stand on one leg. Green button.
Thank you. So my presentation has the following parts. So first is TextME, the introduction, then the TextME overview. Then I will describe how we develop the default material properties and the default low spectral information, because these are very important to make the program more practical and more convenient to use. And after that, I will use the field test section to verify the TextME program, to compare the TextME prediction with the field survey, use the real test sections. And after that, I will use the default value to demonstrate the case studies to show the default value, how influences the TextME predictions. And finally, the conclusion and summary will be provided. Introduction. For several decades, TechSouth has been using the FPS, the Flexible Pavement Design System, and overall it serves well, but with some limitations. For example, it uses only modulus for material properties, and only use the annual average temperature for the climate input, and use the ethos for the traffic input. So there's not much details in the FPS will consider. But we all know this detailed information make differences. For example, if the asphalt mixture has the same or similar modulus, but has superior engineering properties like the rotting resistance or the cracking resistance, the current FPS cannot determine the benefit for the performance. Also, the recent developments have provide opportunity for more rigorous and more rational pavement design procedures. For example, now we have the hourly climate data, we have the low spectra, and also we have more advanced material models, and also we have more advanced computer technologies. So in this environment, TextME was developed at the end of 2014. Actually, it's about more than 10 years effort since we started the NCHRP 1-41, the reflecting cracking model, worked with Dr. Litton, and also the NCHRP 1-52 for top-down cracking. So it's about 10 years to make this program work. After that, we have 4 years pilot implementation in Texas. And now the program can be standalone or can be connected with the current FPS. So here is TextME, the main screen. So basically, in this screen, we have 4 types of inputs: the structure, the climate, and the traffic, and the reliability. In the following slides, I will describe a little bit details about the input screen. So here the structure input screen. So basically, we have several material type icons listed in the screen. Users can drag these icons and drop to build the pavement structure directly. Then for each layer, users can click the layer and to input the layer thickness and the other material properties. For the climate input, users only need to select the weather station, and the program will automatically load the hourly climate data into the program and will be used to determine the pavement temperature at different depths. For the reliability input, users can input the coefficient of the variant for different inputs, like the thickness or modulus, and the Rosenbluth method will be used to perform the reliability analysis. This method will be faster than the Monte Carlo because the simulation number of the method is much less, so it will be much faster. And the traffic part, I will have more screens in the later time. So for the connection with current FPS, so the left part of the screen shows the FPS screen. There will be a button called TextME check, in the LPS screen. Users can click this button and will launch the TextME. And the input and output of the LPS will be automatically imported into the TextME program. And with that, users can add more details, like the detailed material properties, climate, and also the load traffic thing to make more accurate prediction, and use that prediction to check the LPS results. So to make the program more convenient and more practical, we try to develop the default value system. For example, for the material property default values, we have developed the properties for almost all Texas typical mixtures. And in this study, we focus on the influence of the RAP-RES contents. So here is an example for the test matrix to determine the default values. So you can see here is that, for example, this is type D, this is dense gradient. We have different binder, and then for each binder, we have different RAP content and also different RES content. Similarly for the SMA for different binder. So this is a test matrix we did, and to try to find some relationships for these material properties. So here shows the example for the dynamic modulus. So this equation has the two parameters. At least there's a parameters for the P-RAP. P-RAP is a percentage of the RAP, and the P-RES is a percentage of RES. That's the RAP-RES content, and based on that, we can determine the dynamic modulus. So in this plot, it shows the equation. The equation predicts modulus compared with the lab-measured modulus. So similarly, we do this test for the fracture properties and the rotting properties. So we develop these default material properties and incorporate these values into the program. So here we show the input screen for the material property. So users only need to choose binder, the PG grade, and the gradation, like type D, type C, and the RAP content and the RES content. Then the dynamic modulus and the fracture properties and the rotting properties will be automatically displayed in these items. Of course, if users have the lab test data, they can input this. They can modify these values. But here we provided this default value system. So that will make the program much more convenient to use. Users, it's not realistic. We expect the users always have all complete detailed information. So for the default low spectral info, so we all know that it's sometimes very tedious to prepare and input this low spectral info because there's a lot of numbers involved, like physical class distribution, axial load distribution, Monson adjust factor, and vehicle class distribution. There's so many data. So here we use the WIM station data from Texas and divided this data into different categories. For example, based on the road, we divide it into 4 types of road: interstate highway, state highway, and farm road, and energy section. Energy section is the area we have the gas and oil. So here the table shows the weather station, or the WIM station in the interstate highway. And here, this slide shows this vehicle class distribution. Vehicle class, the percentage, the distribution. So basically, we can see the class 9, the vehicle class 9 is dominant. So we based on the volume of the vehicle class 9, the 18-wheelers, to divide this volume into 3 categories: the heavy volume, medium volume, and the low volume. And similarly, for the axial load distribution, we also divided this into 3 categories: the heavy axial load, medium axial load, and light axial load. Because the axial load is different with the volume. although the truck can be empty or can be full. So the actual load is different. So basically, in the program, users only need to select the highway type and the vehicle class distribution type, like high, medium, or low, and also the actual load type. Then the vehicle class distribution numbers and the actual load distribution monthly adjustment factor, and all this information will be incorporated, it will be loaded up in the program. So users do not need to input any numbers. If users have the WIM station and have the detailed numbers, they can edit and modify these numbers. So to verify the program, we identified 11 test sections in 6 districts. For each section, we collected the material for each layer and conduct a lab test to determine the material properties, and also to collect the traffic information and input all this information into TextME and to make predictions. Also, we conduct a performance survey. We want to compare our prediction with the field performance, with the survey results. So here is some photos. When we collect the materials, and also this is some photos when we do the measurements, like the rod measurements and the crack measurements. For the traffic, when we assemble traffic information, there are 2 resources we can use. First, we can use the text out the statewide plan map. So in this map, for each road, users can get the information like the AADDT value and the truck percentage. So based on that, we can calculate the ESOS. Or we can use our portable WIM data. We put the sensors on the road and to collect the detailed load spectrum information, use this portable WIM station. So this is in the real test section, SH6. So I will compare the SH6 to present that comparison results. So basically for the 11 sections, there are more than half of them, because the time is not long, there half of them didn't show any rod depth or any cracking. And also our prediction also didn't show at this time, didn't show any crack or rot at this time. For the test sections like SH6 and SH7, the section 1, and FM 3549, we did see some failures, like the first 2 had the rod depths, showed the rod depths, and this one showed the thermal cracking. So here, the green line is the measurements, is a field survey. We do the survey, averagely it's twice a year, so once in the summer and once in the winter to get the survey results. And this line, the red line, is our TextME prediction. And for the SH6, see, we have both use the ESOS or the low spectral information, use the portable WIM data. And this is the comparison for rod depths for SH7 section 1. And this is for the FM 3549 for the thermal cracking. So basically it matches pretty well. And here for the case study, we use default values. So we assume a standard, a typical pavement structure and like weather station. And we only change it here is the wrap content. Is the wrap content. So the wrap 5%, 20%, 10%, or what I cannot see, but 5, 10, 20. Okay. So here is show the TextME prediction for this is a month. This is the rod depth. So at the 20 years, end of 20 years, there's a different rod depth. So basically, if you have the higher wrap, you will have a lower rod depth, and then also you will have less cracking life. So here, 50% fatigue cracking rate as a like failure criteria. So here is a 36 months to failure. That's the fatigue cracking life. So basically, the higher wrap, you will have less cracking life, but less rod depth. And here we use the different VCD. We compare different vehicle class distribution. So similarly, if you have a higher volume, you will have less, or you will have higher rod depth, but you have less cracking life. Similarly, for the heavy axle load distribution, the heavy axle load distribution, you will have higher rod depth and less cracking life. So here the summary and the conclusions. So in this study, we developed the default material properties and the default load spectra and incorporate into the taxonomy to enhance the
Okay, AT&T is telling me it is 3:40, so we've got our 11 minutes. Let's go ahead and take our seats. Okay, we have had a great summary of some things going on around the U.S. We've seen a couple of presentations on Pavement ME. We've seen a couple of presentations of states that are doing their own mechanistic empirical design procedure. Now we're going to go for an international flavor for mechanistic empirical design, a couple of presentations related to work that's going on around the world. The first of these is Eric Denneman. He is with the Australian Asphalt Pavement Association, and he's going to bring us an Australian perspective to mechanistic empirical design. Eric, help me welcome Eric.
Thank you, Kevin, and good afternoon, everyone. I really appreciate the invitation to speak at this great forum. I'll be giving you a brief presentation about mechanistic empirical pavement design in Australia. I'll start with just an overview of the Australian pavement design method as it stood in 2012. And that's not because that's the year I arrived in Australia. You may have noticed by now that I'm still working on my Australian accent. But that is because that was the previous version of the Austroads design method. So a number of improvements were made, including the outcomes of the Australian Asphalt Pavement Association's Asphalt Pavement Solutions for Life project, which is basically a perpetual pavement design concept. There were some other improvements made to the Austroads, which were included in the revision of 2016 that I'll be quickly running you through. And some of the road agencies have really gone all the way, and they are now using those improvements to have asphalt mix specific modulus and fatigue models to use in their pavement designs. And finally, I'll have some conclusions. So back in 2012, and actually still to this date, the Australian Asphalt Pavement Design method was mainly based on the Shell Pavement Design Manual of 1978 that some of you may be familiar with. And what we were seeing in 2012 was that with the ever-increasing design traffic loading led to ever-increasing asphalt pavement thicknesses. Just to give you an idea, in the great state of Queensland, where I'm from, or where I live, they were seeing designs of 400 millimeters of asphalt, so that's what, 16 inches, up to 600 millimeters of asphalt, so that's 2 feet of asphalt. Which, contrary to what you may expect, was not welcomed by the asphalt pavement industry, because that meant that the white stuff that shall not be named became more competitive. And that was especially true in the warmer regions of the country. Now, that's not necessarily the fault of the Shell pavement design method, let me state that clearly. It was more the implementation that was used in Australia. One of the issues was that to determine the modulus, they used indirect tensile resilient modulus, and they had a very simple, so that was done at a single load frequency and a single temperature. And then there were very simple functions to predict the modulus at different design speeds and at different temperatures. And to estimate the flexural modulus. So flexural modulus is what's used in the Shell pavement design method. And when it comes to asphalt fatigue prediction, many people wouldn't like to admit this, but what was in the Austroads guide was basically just the Shell laboratory model, which was developed for 12 mixes in the 1970s, tested in laboratories by Shell in Europe. And that model was used in the Austroads design method unchanged. The only thing that's in there is a laboratory to field shift factor, which for the major roads was 1. So basically we were predicting that the fatigue performance in the field was equal to the fatigue performance in the laboratory of a beam. So that's as it stood in 2012. So against that background, the Australian Asphalt Pavement Association started the Asphalt Pavement Solutions for Life project, recognizing that the Austroads method led to various conservative designs, again, especially in the warmer parts of the country, and also looking at the international evidence that was suggesting that above a certain pavement thickness, classic bottom-up fatigue cracking that we're designing for does not occur. So they were looking to introduce the fatigue endurance limit concept in the Austroads pavement design method. These were the research objectives for that project, and I will say that with the benefit of hindsight, it was maybe unfortunate that it was so focused on dynamic modulus, the dynamic compressive modulus, because that's not very compatible with the Austroads pavement design method, which uses flexural modulus. So it was very heavily focused towards dynamic compressive modulus, developing of a database for typical Australian mixes, coming up with a laboratory to field interconversion for that modulus, and then also determining the relationship between dynamic modulus and current Australian test methods, so that would have been the resilient modulus and the flexural modulus. Unfortunately, that's not easy to do. Developing a robust relationship between flexural modulus and resilient modulus is quite straightforward, well, we've published the best we could do in terms of coming up with a relationship between flexural modulus and dynamic modulus, but it's not a very robust relationship. And why that matters, I'll come back to a bit later. And then they developed a recommendation. The objective was to recommend a method to incorporate the fatigue endurance limit into pavement design. So there was a lot of work done on dynamic modulus testing for typical Australian mixes. Won't go into that. But this is, I think, the most important part of the work that was done. That was identifying the fatigue endurance limit, and they looked at a very wide range of actual field performance data from across the world. So there's NCAT sections in there, there's outcomes of the UK Velman project, which basically looked at the whole road network in the UK, and then there's a lot of Australian sections there. And basically what they tried to, so all those sections have carried a lot of traffic for a long period of time, and what they were trying to identify there was the boundary between where sections start to crack and which sections don't crack. And that was expressed in terms of the modulus of the material and the fatigue strain that was, or the field strain, so the horizontal strain at the bottom of the layer as calculated for those sections. So they determined that boundary between cracked and uncracked section, and then also came up with an 80th percentile confidence and a 95th percentile confidence limits for that fatigue endurance limit. So that was a lot of work. And the final outcome of so APA recommended this fatigue endurance limit for inclusion in the Austroads design method. It's the function that's shown here, where K1 is equal to 1 for the 80th percentile, and K2 is an adjustment factor, which is 0 for conventional mixes. So basically the fatigue endurance limit just becomes a function of the stiffness or the modulus of the mix. Now in terms of incorporation into our national design method, that did run into a couple of problems. Like I said, the procedures they followed were very heavily geared towards the use of the dynamic compressive modulus, which is not really compatible with the Austroads design method. And as a result, all that could be done was run a lot of comparative analysis. And in the end, the road agencies were only comfortable with introducing a maximum design traffic limit in the design guide based on some of this comparative analysis. So basically the agreement is that you do not design your pavements for more than these maximum design traffic limits, and therefore you're basically limiting the thickness of your asphalt pavement. Those limits are temperature dependent, and that is to recognize the influence of modulus on that fatigue endurance limit. It is also a recognition of the fact that the states in the south of the country, where it's a little bit cooler, were more comfortable with the thicknesses they were getting out of their design method than the states further north, where it's warmer. So I have I've put the design temperatures there in Celsius and Fahrenheit. Basically, so for Queensland, you would be designing pavements for no more than 200 million equivalent standard axles, which seems like a lot, but if you consider that pavements in Australia are typically designed for 40 years design periods, that's not unheard of. Okay, then in terms of the other improvements that we made to our mechanistic empirical design guide, we improved the characterization of the design modulus. We corrected the way we test our mixes for fatigue to be more to better correspond to what the ideas or the models by Shell. And we also improved the modeling of heavy vehicle standard axle groups, but I won't be able to discuss that due to time today. So in terms of modulus, it is now possible to directly measure the flexural modulus and use the flexural modulus master curve in pavement design instead of those resilient modulus assumptions. And what that does is immediately reduce the pavement thicknesses for the pavement in the warmer parts of our country. What I've shown in this graph is the resilient modulus result, so that's the dot, and then the predicted resilient modulus at different load frequencies, as it used to be done in the Ostrow's design method. That's the dotted line, the straight dotted line. And compare that to the flexural measured modulus, which is the continuous line, and you'll see that at the lower loading frequencies or the higher temperatures, you get a higher modulus, which corresponds to thinner pavements. Then, in terms of fatigue, we had a problem. You may be familiar with the discussion around Haversine and sinusoidal testing in fatigue testing. So that's the fact that under Haversine loading, Haversine displacement loading results in a sinusoidal strain response in the sample after a number of load repetitions. Now that's not a problem if you've used your Haversine testing to calibrate your fatigue models. Unfortunately, what we had in Australia is we were using a European design method, which was based on sinusoidal testing, in combination with a US test method. The test method in Australia was based on an early version of AASHTO, used Haversine loading, and as a result, the difference in definition and strain in the test method and the design method was a factor of 2. So the solution was quite simple. We just changed to the European test method. So what all of this does, what all of these changes do to the Australian design method is that it now allows the use of mix-specific modulus and fatigue models, so you can characterize your material. Some road agencies allow contractors to characterize their material in the laboratory, come up with a modulus master curve and fatigue function, for laboratory function for their material, which I'll show on the next slide how we do that. So we test 27 beams divided over 3 temperatures, come up with a fatigue laboratory model for that particular material, as is shown. Well, the function is shown at the bottom there. So basically, the fatigue performance becomes a function of the strain level and the modulus of the material. And then you replace that Shell laboratory model, which again was developed for 12 mixes in Europe that have very little to do with current Australian mixes, with an actual model that was developed for your material. So in conclusion, we've stopped the trend of increasing pavement thicknesses, provided that that these concepts are being used in the design. That's also because we've introduced EME2, high modulus asphalt, has also contributed to that. And I know that there's work being done in the US on introducing EME2. I think that's great. By the way, don't go putting polymers in there. The most cost-effective solutions you can get by just using straight harder bitumen. That's a side note. Perpetual pavement designs are now considered for major projects, and I hope that in the panel discussion we can have a bit of a discussion around that, how that's being done in the US. The discussion I have with road agencies generally for their major project is, can you really afford not to make this pavement a perpetual pavement? The difference between a perpetual pavement and a 40-year design life is typically something in the order of 50 millimeters of asphalt, so 2 inches. And that is not a major cost on those projects. And we've also, by introducing the mix-specific modulus and fatigue functions, we have now created an opening for advanced asphalt mix technology like EME2, get the full benefits of EME2 or other polymer-modified high-performance mixes. Thank you very much. I would just like to acknowledge the team that worked on the asphalt pavement solutions for life, because that was not me. But thank you very much.
Adam Hand, University of Nevada. Eric, nice presentation. I'm curious, you said that you changed what you're doing in terms of fatigue testing. Did you, or maybe the question is, do you condition your specimens before testing other than short-term aging?
Thanks for that question, Adam. The answer is no, we do not. And the reason for that is neither did Shell. So in your test method, you have to be true to the models that you're using. Understand all the consideration for aging your specimens, but we don't.
Thank you.
Thank you.
Okay, so our final formal presentation before we get to the panel discussion will be brought by Jerry Huber with Heritage Research Group in Indiana. Jerry is no stranger to this group. He's going to be telling us about the perpetual pavement concept and approach in China. So please help me welcome Jerry Huber. Jerry?
Thank you, Kevin. So I'll talk to you this afternoon about specifically about a trial project that was done in China. This is in the Shandong province. This is a typical interstate pavement. In this particular case, 2 lanes in each direction, and with a visual barrier separating the lanes. These are typically built on fills, somewhere around 6 to 10 feet of fill, so most of them are in the air. When these pavements were first being built in the 1990s and early 2000s, the traffic on them was relatively low, but within just a few years, 5 years, they were seeing very heavy levels of especially truck traffic and very heavy trucks. This being just an example of a 4-axle truck. You'll notice that there's just one drive axle on that tractor unit. The impact on the roads was substantial, and behind that blue truck you can see an area where there's that pavement is fatigued, and there's pumping of the soil cement base that is coming up. And just to show that it's not just asphalt pavements that were having difficulty standing up to this, here you can see a concrete pavement as well. So a perpetual test pavement was built in 2005, and this was a joint cooperation project of the Shandong Department of Transportation, Shandong being one of the provinces in China, FHWA here in the U.S., NCAT, the Indiana DOT, and the Heritage Research Group. This was taken in November of 2004 on top of the completed subgrade before the paving started. Now, I'd point out to you the information that we had about truck loads. Now, these are gross vehicle weights, so these are not axle loads, but a 5-axle truck in the United States is limited to 80,000 pounds. And you can see that in China, the 5-axle trucks, that only 27% of the trucks are less than 80,000 pounds. And if you take that line upwards, you'll find that the 100th percentile is 112,000 pounds on 5 axles. So these are much heavier loads than what we're used to seeing. So the design loads that we ended up using were these ones when we analyzed the traffic information that we had. And you'll notice, for example, the tandem axles on a 5-axle truck, the design load, which is the 90th percentile, is what we chose from the data that we had, is 76,000 pounds. So that's almost equivalent to the gross vehicle weight of an American truck. Now, this information was analyzed using per road, and the traffic, the materials, the performance criteria were analyzed using per road. Now, in terms of the distribution of vehicles, the bars in red is all of the ADT, and the ones in blue is the heavy truck traffic. And so we were able to use that in our analysis. We had materials characterization along the route that we had. It was approximately, how long was it? Somewhere around 3 miles. We built 5 sections. Each of them was about, they varied in length, but they're half a mile to 3/4 of a mile in length. And the difference in length was because of bridges. We built between different bridges. We didn't have a lot of information on the HMA modulus. We did have weather conditions, and we were able to convert that into pavement temperatures. We were able to select a equivalent modulus for the HMA. The design methodology, and by the way, this evaluation of materials and per road, et cetera, I really need, these are David Tim's slides, Dr. Tim. So this is his work, his part of the work that I am presenting to you. The analysis that he used was, the standard type of thing, tensile strength at the bottom of the HMA layer and vertical compressive stress on the lower layers. So this ended up being the three, in China they called the American test sections. So there was 3 of the sections. One was built, you can see, to 70 microstrain as a limiting. 2 of them were built to 125 microstrain. The difference with the 125 microstrain is that one had different considerations for both the base layer, which is a polymer modified asphalt binder, and the subgrade modulus. Now, putting that into the context of all 5 sections that were built, there you can see the 3 U.S. sections, and you can see the 2 China sections. So the 5th one is the design that was being built. So that became our control section. And the U.S. ones are built directly on top of lime-modified soil. The 2 China ones have pozzolanic layers, cement-treated layers between the lime-modified subgrade and the HMA on top. So you'll notice that test section 4 has quite a bit thicker HMA, but still has the pozzolanic layers. Test section 5 has quite thin, it's about 6 inches thick, of HMA over top of cement-treated base. So some pictures of construction. These were built with a batch plant. This was a brand new Chinese manufacturer batch plant. The control systems were pretty much what you'd expect to see in the U.S. for a new hot mix plant. Computer screens and that. By the way, that gentleman whose shoulder you see and neck and shoulder that you see wearing that white shirt, that's the plant operator. And that shirt was as white at the end of the day as when he came in the morning. And just to further impress you, there's the floor in his control room. So if you wanted to come in and talk to him, you were required to take your shoes off, and he didn't want your sweaty socks on his nice polished hardwood floors. He had some bathroom sandals there for you to wear. Field laboratory was kind of like you'd expect to see in a lot of places. This was Marshall mix design that they were using. You can see the Marshall hammer there and some scales. They were using an NCAT burn-off oven for evaluating asphalt content. Here's what the aggregates look like. They were quite a hard limestone, a fairly high specific gravity limestone. There's the stockpiles of aggregates, pretty much a very good quality operation of a hot mix plant that you'd expect to see of any good quality contractor in the U.S. or anywhere else. Cold feeds were typical kinds of cold feeds that you'd expect to see here in the U.S. The haul trucks, they did a very good job of loading them in 3 dumps, as you can see. But it's interesting, that truck is carrying 45 metric tons of hot mix. So that on 3 axles, you've got about 115 to 120,000 pounds of load on that truck. Here we are out on the grade. So they chip sealed on top of the lime treated subgrade, and then they applied tack coat on top of that chip seal. There you can see the trucks lined up and ready to be discharged their mix. They used echelon paving, so they had 2 pavers to pave the full width of inside shoulder, 2 lanes, plus outside shoulder. So they paved all at once. These were very large pavers, and I don't remember the model. Well, you can see it's an Ingersoll Rand Titan 525. If you want to go and look it up, at the time I think it was the 2nd largest one that they made. I know that when the paver was empty, you could easily crawl through the tunnel from the hopper back to where the screed was. It was big enough for a person to crawl on their hands and knees. We installed gauges into the test section. Here you can see the paving over top of those gauges. This is one of the 15-inch thick sections when it's completed. This is what the project looked like when the construction was done. So this was built in the summer of 2005. Now, what we wanted to do with these sections is to acquire some data. So essentially what the experimental process was to calibrate those pavement sections so that they almost became like strain gauges. In other words, what we were planning to do is to run trucks of known weight across the pavement where the gauges were in each of those different 5 sections, do that at different times of the year when the temperatures are different, and you can get a curve of for any given load, you can get a curve of strain versus temperature. So here you can see one of the trucks that we were using. So that truck had 60 metric tons of aggregate on those 3 back axles. And the idea was that you can see there where it says triple axle and 42 tons, 48, 54, and 60 tons. Those are conceptual lines, by the way. That is not data that you're looking at. But the idea being you would expect to see as the load goes up, of course, that the strains go up. And you would do this at different times of the year, and you would come up with different temperatures. And then on the lower right-hand side, you can see a strain distribution for that pavement. So this is what those curves ended up looking like. Because of the fit of the data and everything else, they're not quite as nice as the conceptual lines that you saw on the previous slide. And I'm just going to go through quite quickly through the 5 different ones. But there you can see the 4 different loads, the 42, 48, 54, and 60 metric tons for each of the different sections. Section 2 and Section 3 and Section 4. And now the thing to note about Section 5 is all the other ones had been about 100 microstrain and less. And Section 5, you'll see that at a pavement temperature, and this is a mid-depth temperature for the pavement, it's operating in the 250 to 400 or 350 microstrain area, so substantially higher microstrains. Then what we were able to do is to analyze the pavement response and determine the longitudinal strain, transverse strain, and vertical stress on the basis of thickness, load, the offset from where we were, the temperature, and the speed of the vehicle. So we had weigh-in motion, so we had speed distributions of trucks of different weights. There was modeling that was used to fit and come up with a model for those pavements. And then we collected weigh-in motion data for 2 years. And we got distributions of actual weights that were going across. Now, that previous graph that I showed you was gross vehicle weight. This graph right here is tandem axle weight. So this is the distribution of measured tandem axles over the course of a year and a half. Now, the 90th, so our design was 76,000 kilograms, or 76,000 pounds, I'm sorry, on a tandem axle, which, by the way, one of the presentations earlier in the pavement design, I believe it was in the Texas presentation where they had traffic characterization for light, medium, and heavy roads. I very quickly looked in that table and saw that for the interstate highways in Texas, that the design axle load for a tandem is 26,000 pounds. Here you can see we designed at 76,000 pounds, and we're dealing with 105,000 pounds as the 90th percentile. So what came out of all of this? Basically, Section 5 ended up being not perpetual, and all the other 4 sections ended up being perpetual. And so on the basis of that, after 2 years of research, they actually made changes to their structural design in the province because they were still in a very large building mode for their interstate highways at that time. So long-lasting pavements can be built to last as long as maybe the China's Great Wall. Thank you.
Jerry Reddy, a very good presentation, really interesting work. Zhang Pinyu, Michigan Technological University. One quick question is, you measured the strain. I think the strain measurement is pretty challenging. I think back in 2005, I think how you really managed to make sure those strain gauges are functioning well and under those heavy loads. Of course, I think that's, I would assume it's a tensile strain you're measuring, right?
Well, the better person to answer that question would be David Tim. And essentially the role that NCAT played was the instrumentation and the collection of data. That was a huge role in this whole thing. So I have as much confidence in the quality of the data, strain data, as in the quality of the strain data at the NCAT test track. Oh,
yes, thanks, Jerry.
David.
So one of our big concerns, of course, were these extremely heavy loads, what Jerry was showing there. And what we found, of course, is if you put 20 inches of hot mix over a strain gauge, it'll do pretty good. The 6-inch section where you've got a strain gauge underneath those kind of loadings, that section you didn't have any pictures of it, but I know you've been back to visit that particular, the section S5, and maybe you could describe what it looks like, but there's a tremendous amount of deformation. I'm not sure if the gauges probably aren't working there anymore, but that section experienced a tremendous amount of bending and a lot of deformation.
Yeah, and of course those gauges were only 6 inches from the surface because the HMA thickness was only 6 inches.
All right, great. I hope most of the strain gauges basically survived in the entire testing. I would assume so. Thank you.
Yeah.
Jeff Rowe with Abatec. Jerry, I don't know if you recall, but we also did some analysis on those sections to look at the strain magnitudes we'd calculate versus those that were being measured. And, the trends were absolutely consistent with the measurements thereabouts. I mean, you're going to get some scatter because of the daily variation in temperatures and things like that. But, the trend that we got sort of confirmed that those strain gauges were doing what we wanted and the pavement was behaving as you expected to see it.
Yeah, and I would add too, and Jeff, thanks for bringing that up because I totally forgot about that aspect of it in answering it. But a follow up to that would be, so these were built in 2005. In 2007, they built a trial project using the criteria that were coming out of the test sections. In 2016, I had the opportunity of visiting that section. There's nary a crack in it after 9 years. So it performed very well for them. Okay.
So stay here, Jerry. So what I'm going to do is call the authors and speakers up to the front. We've got a healthy amount of time here left. If you didn't get a question asked or answered, now is your time. We've got plenty of time. We've got an esteemed panel. Go ahead and have a chair. And we've got an esteemed panel here just waiting to talk to you about mechanistic empirical design, perpetual pavement design, how Texans react to just chilly weather to the rest of us, whatever the case may be. So, any questions? Yes.
Mansour Solomon, Empire State. Harold, I've got a question for you. If I remember correctly, you mentioned, maybe when Gail asked about which DOTs are using it, I think you mentioned maybe 5 or 6 are kind of routinely using it, right? So if I am not mistaken?
Yeah, about
Okay.
6, half a dozen.
So I saw the Virginia presentation on the process they went through calibration. What I wanted to hear from you is the ones that you mentioned are routinely using from national coefficients to local calibration. How much effort was there? How significant these differences were? And eventually, where did they end up? Did they end up with sort of correlations that we saw at Virginia, or were they better, were they worse, or what's going on there?
Yeah, most of them, the effort varied significantly. We have some like Colorado, Arizona, and to some degree Pennsylvania. They did, and Georgia, did a lot of field investigations. Others did very little field investigations. They just went with what was reported there. I think the field investigations are extremely important. I think there was a question asked about the variability on the fatigue cracking. Well, we found the same thing like in Georgia, a lot of variability between predicted and measured fatigue cracks, and then you do the investigation and you start pulling cores and you see some of those that had high percentages of cracking. You see that's all top-down cracking, and it shouldn't have been in the bottom-up cracking category. So I think field investigations, even though they're expensive and they take time to do, they're well worth the effort and tend to explain some of the variability that we see between predicted and measured values. Most of the calibration the local calibration that's been done to date also was done with some of the earlier versions, kind of like what Virginia did. Some of those agencies are planning to redo their calibration with the calibration tool or so. And the reason for that, what they found is, from a rutting standpoint, they found differences. And that's because we know that we've over-predicted rutting with their earlier versions. And there's basically 2 reasons for that. One reason is a lot of the initial repeated load plastic deformation tests were all done unconfined. And so the exponent above the end term, was like the 0.47, which is a very high slope. And that value decreases significantly with confined repeated load testing. So I would say most of the calibration work that was done with the earlier version states saw changes to the global calibration values. NCAT did a summary of a lot of the local calibration factors that had been reported about 2 years ago, Randy? About 2 years ago. And that report is readily available, and it shows significant difference across the country. But I think once you start bringing in the laboratory measured values, that some of that dispersion across the U.S. starts to decrease.
All right. Thank you.
Thanks, Harold. Appreciate it. Yes.
Mihai Marastanu, University of Minnesota. I have more of a general question. Is there any study that... Are there any studies that look at tangible benefits? Okay, so I had used this version of Pavement Design, and then I went to the next version of Pavement Design. I improved, I've done calibration. It matches, the predicted versus field data better. But ultimately, what is the result, the tangible benefit? Are you going to build thinner pavements? Are you going to repair them less frequently? I mean, does anybody, is there such a study? Because I understand, you know, the science behind it is great, but I'm just trying to understand, we keep improving and improving, so what exactly does this translate into?
Who wants to take it?
And I'm not criticizing, I think this is great work, but I'm just trying to look at in the long run, so.
Okay. John?
So I think if we're just using the same materials under the same traffic, meh. But we're changing the materials. We looked at polymer modified. We're looking at the rubber mixes, the rich bottom mix, the high wrap mixes in our AC long life, and using a stiffer binder, which we learned from the Australians back in the day, and the French, and now using high wrap for that, and our change from V mix design to super pave mix design. And we can't, supposedly, and I believe that in the vast majority, those are improvements in the materials properties. We cannot take advantage of those materials properties without having these design systems and trusting them, verifying them, validating, calibrating, and trusting those shift factors that when we then change the materials properties, we feel we have a pretty good idea of what that's going to do. And if we don't have these mechanistic empirical design methods, we definitely don't have enough APT devices to figure this all out. We understood that 15 years ago. We can't take advantage of these things unless we want to wait 40 years to see how they did and update our empirical method. So that's where I see the main advantages coming from. And the other one for us has been, going back to the previous presentation, we've made changes in our construction compaction requirements and being able to use these to come up with essentially our pay factors and understanding the effects of our better compaction, and then incorporating super good compaction into our AC long life. So I think those, to me, we can life cycle cost those, and we have in some cases, and it definitely shows a payoff.
Oh, great answer. Thank you.
Thank you. While you're, Randy, you're going to, okay?
Randy West, NCAT. A little bit off subject, but since we have such a distinguished panel up there, I thought I would go off on a little tangent here. Thinking about automated vehicles, automated trucking, I'd like to get your thoughts on how we should evaluate what that effect might be on our current pavements and then what we might do going forward. Anybody want to touch that one?
Truck platoons, who wants it?
So, I mean, I've thought a little bit about this, and I think there are several different things that could come about as a result of this. One of the things, of course, on autonomous vehicles is if it's a machine that's steering the vehicle, perhaps it's more precise than what a human is, and so we worry about, we know as from wheel wander, the impacts of concentrating loads near the center. Now, in my view, that, you know, that's easily addressed from the point of view that manufacturers can design typical normal wander in and increase the standard deviation of the wander equally as well as they can in holding it still. You know, you just limit the amount of horizontal acceleration. So yeah, you're not trying to put the passengers to sleep. So that's one thing. The second thing is the repetitive loading. Certainly having trucks that are 50 feet apart instead of, you know, a couple hundred feet apart, or however they normally follow, or 100 feet apart, is going to reduce the rest time, the rest periods between axle applications, and that's going to make a difference. But I strongly believe that we have the ability, with the tools that we have in mixed characterization and mixed design as well as structural evaluation, that we can address those however they may turn out to be.
Absolutely.
This is Shenhu from TGI. We just conduct research about the autonomous vehicle. We just use our program to compare if the autonomous vehicle has no wandering at all, compared to the normal wandering, the rod depth can be like 30% more than the usual wandering.
Wow. Okay. 30%. Yeah, John.
We've been working with the transportation folks, and one of the things that folks who've been in the industry, automated vehicles, I don't believe are going to happen overnight in the next 5 years, because first of all, until you get to about 60% vehicle-to-vehicle communication, you actually are going to increase congestion because you have to reduce. You can't vehicles spread apart. Humans drive closer together than the automated vehicle technology allows it. Until you get 60% vehicle or 70% vehicle-to-vehicle communication, you have some major issues with this. So just a dose of, I know the hype's super high right now, but the general discussion among those who are really studying it is that automated vehicles are going to happen in increments in controlled facilities, truck-only lanes that require vehicle-to-vehicle for a while. So I think one of the other things that's not on our radar is electric vehicles, because if you scale the battery, a Tesla weighs 8,000 pounds, 7,000 pounds, whereas the comparable gas vehicle weighs about 40% less. Big issue in California now is semi-tractor trailers going electric, and how are they going to distribute that battery pack weight on that back axle of the tractor? So I think I would like to put that on the radar, which I think at least in our state is going to happen faster. And there's pressure already. There's legislation to increase axle load limits.
Adam?
Adam Hand, University of Nevada. And John, this question's for you. You know, Caltrans has really been a leader, and you talked about CalME and long life pavements and actually doing designs before you go to construction and you know, being able to use that information to validate your designs. And my question is about the construction side of that, the acceptance process, and I know that you know, you're using some tests that the local consultants may not have, you know, in their back pocket, and so I'm curious about how that implementation has gone and what has worked well and what has been a challenge.
So our first implementation, let me back off of the long life pavements, which is where that's happening. Our first implementation issue is because we've lost that corporate culture of actually designing pavements because of lack of money in large degree. There's a general perception that the empirical method is well calibrated and actually predicts, you know, the thickness that we need for the design life, not understanding that our empirical method was last calibrated in 1966 with the ASHA road test data. So that's our actual biggest obstacle right now. Because CalME's coming back with thinner sections for the long life pavements than the empirical method, and they're scared of that right now. Tying to performance related specifications, what we're trying to get to is we want to get those tests out of the university laboratory. We basically need a critical mass, not one every 3 to 4 years, so that the industry can amortize those guys. We've simplified them quite a bit. I think that the more complicated design will be done with the actual material, actually following basically the Australian idea. For the more expensive designs, you'll actually test your materials, and we will try and, we're trying to get to a place where we're writing more of the performance-related specs that we accept the mix based on the performance-related test, the more complicated one. We will never construction quality assurance on those tests. We need surrogate tests that are simpler, faster, cheaper, and are indicators that something's changed so that we can stop and figure out what's going on that aren't giving us the stiffness and the fatigue life and stuff like that. So that's kind of the general direction.
Thank you.
Yes, please.
This is Emin Kutay from Michigan State University. John, sorry, this question's for you too.
Throat lozenge, so I'm doing better.
Strain hardening approach that you mentioned in the CalME.
Time hardening.
Time hardening.
Yeah.
So that is in fatigue also?
That is in fatigue also, yes.
So in those approaches, the sequence of loading matters quite a bit. So how do you make it? It does.
We're walking through the axle load spectra and the axles for 4-hour increments, and we update after the 4-hour increments. The difference in changing the order of those loads within the 4-hour increment is not actually that great because we're actually doing pretty small increments to do this. We've not really, we looked at it initially, did not see major differences compared to the other variabilities and things that are inherent in construction as much as anything.
Maybe Harold can also chime
Sorry?
in. Harold, in Pavement ME, it makes a huge difference, actually, the approach. Do you know the sequence of loading, whether you apply the single axle first, tandem, tridem, and the load levels, which one you start, which one you apply in rutting calculations, essentially?
Yeah, it's not so much with what John referred to in his 4-hour increments. And it's more, I guess, on the rehab side where the time hardening is used in Pavement ME. But you do switch, kind of like what John mentioned, but I don't know whether it starts with the smaller vehicle or heavier vehicles, but it has the 5 temperature quantiles, I guess, and it does each one of the quantiles, but not in a 4-hour increment. It does it more on I think it's, with the rutting, it's more on a monthly basis.
Okay. Yep.
We did some for the load spectra, actually the load sequence can be different, but we have some theoretical deduction. There's no difference between if you add a different load sequence. Like for the rut depths, to calculate that when you use the superposition method, and if it is a linear way, and whatever you add your load spectral info, like you use heavy load first, then the light load first, second, then there's theoretical calculations. The sequence doesn't matter. We have a paper of that for the rutting calculations for the superposition way.
Can I just make a comment?
Quickly.
Quickly. I find it very, very surprising because if you think about the 5 different quantiles, if you start with a very high temperature, with a high load, those curves are like that. So you're going to start with a very high rutting or whether, so, that should matter quite a bit. I find it very surprising that it doesn't matter. So.
Okay. You want to respond?
Yep. Yeah, I would agree. It matters. How much it matters, I'm not sure. Especially, it probably mattered more on using the very high exponent for the number of load cycles. That's about 0.47 or so. It probably matters less if we're talking about the confined tests that are about 0.22.
Okay.
I think, I agree with the comments. So I would like to clarify here. So for when we do that, we assume the monthly average temperature doesn't change. So in that case, when the temperature didn't change, so at that time, the load sequence doesn't matter. Thank you.
That's a good clarification. Frank Fee, LLC.
Frank Fee, yes. In 2000, we put together a TRB, a couple of sessions on perpetual pavements. And John was part of the ones that contributed to it along with other people. And I just want to report on the one that we did on a heavily traveled New Jersey road where we took on that job. That road is now coming up on 50 years old, and it has had 2 4-inch overlays in the time zone of the current. And currently, the last one was done in, I think, 2011, something like that. And as far as I know, it's still in good condition. So they were 2 polymer modified overlays, but the material, if you've got it in the ground, if it's there, and it holds up, guys. It does the job.
Thank you, Frank. Adam?
Adam Hand, University of Nevada. I'm going to go back to John because, John, I really asked you a two-part question, and one of them was, what are some of the positive things you've seen and some of the challenges? And I stepped away and I thought about it for a minute, and you kind of focused on the challenges. So I know there have been some positive things that have been outcomes along like pavement, in California. So
I think the first project when the asphalt industry was given a pilot project and the heaviest trafficked road in the state was picked for the pilot project coming out of the ports of Long Beach and Los Angeles, I-710, which was built in 2002. And we didn't actually have CalMe at the time. We were using more of a generic spreadsheet-ish mechanistic design method. But the empirical design method was requiring on the order of, as same issues that Eric was showing, a half a meter of asphalt. So, a lot of asphalt. And they couldn't even construct it in the time windows under the bridges. And by using the mechanistic empirical and taking into account the mixed characteristics of the rich bottom with the 0 to 3% air voids, the stiffened, essentially an EME middle layer, and the polymer modified surface layer, we were able to reduce it from 500 millimeters down to 300 millimeters for the same design easels. Now, that was a 30-year design life. We're now 17 years later, I don't think we've even had any overlays other than the rubber open graded on the surface. Time will tell. I hope I live that long. But I think so far, at least, we saved a 40% decrease in material. Now going forward, our ability to look at our high wrap mixes and incorporate them in to replace the stiffened binder and use wrap to get that stiffness, I think that's another example. So those are just two, I can actually reach out and touch them examples in addition to the more, other magic things that can happen that I mentioned before.
So when you think about the example panel, and I want to use the Pavement ME as the example, at one point lots of somebody said, we need an improved reflection cracking model. So one was developed, it's been implemented. We need an improved top-down model. One's been developed, it's getting ready to be implemented. In the context of your presentations, how do you answer, we need what? What do we need? Where do we go from here? We're just going to pass it down the road. Just going to pass it down.
Thanks.
Like I mentioned in my presentation, not only weed out, most of the state agencies' main work now is maintenance than new construction. So we need a better way to characterize the damage in the existing pavement. That's very important. What is the damage in the existing pavement so we can come up with the correct overlay thickness. That is the one requirement I see in the future. The other requirement is we may have to look at the aging models currently using the Pavement ME because that will have a huge impact on the predicted distress. The third thing is incorporating the preservation treatments. I think that's going to come, but you need to predict what is the service accurately. What is the service life of that preservation treatment to get a clear design life. I think these are the three things I see in the future.
What do we need, Harold?
I would tend to agree with the pavement preservation. What I mentioned earlier was more from a preventive maintenance standpoint, things that get done beyond the early life of the pavement, because pavement preservation can have an impact on the asphalt aging characteristic. That's not taken into account now whatsoever. The other thing, it's not so much in Pavement ME, but in terms of agencies starting to implement it, is one of the things always comes up is testing. You know, how do we run the test cheap and get the right answer?
Okay.
And so I think that's one area.
Hire your local university.
That's right.
Yeah. What do we need? Text in your context. What do we need?
I would like to say, since our model was advanced and also more complicated, so there also the test will be more complicated to get these properties. So I would like to say the default values is really very helpful for users to use and implement and try the system and to get more experience and get more practical use. And also in terms of the cost analysis thing, this is also very important. So when we compare different material, the performance, and with different thickness combinations, so the cost can also be involved and for engineers to make design to choose the most optimum designs.
Okay.
Thank you.
Very good. John, what do we need?
This mostly comes from the questions, but it's since we've been thinking about, we need those cheaper, faster, I would call them performance indicator tests that can point to choosing the data in the standard materials that is based on the more sophisticated test. We need to push the testing out of the universities and into a place where it can function in industry. I think a question was asked of somebody, or asked of Eric, how do you age the mixes to characterize them for the performance-related tests? And we're doing short-term oven aging, so we're predicting at the beginning and then using these models to do everything out. I think we need an intermediate aging protocol to test kind of in the middle of that aging life, so we extrapolate backwards and forwards rather than kind of using a model to predict this whole extrapolation. And I think we really need to do a better job of understanding rest periods. Ties back to Randy's question about AVs, but as I remember back in the old